In this video, we'll be looking at the structure of atom. Lesson objectives. At the end of this video, viewers should be able to define atom, state the composition of atom, define atomic mass, numbers and species, understand the structure of atom by various scientists, their models and their drawbacks, understand the basis of quantum numbers, understand the shapes of various orbitals, understand the rules of filling electrons in various orbitals, and lastly, we solve problems on electronic configurations. What is atom from our concepts? John Dalton in 1808 believed that matter is made up of very small indivisible particles called atom, which can partake in a chemical reactions. Atom can neither be created nor destroyed, but modern researchers have proven that atom is not indivisible. This is as a result of the discovery of radioactivity. The modern structure of atom is as a result of the concept of quantization of energy and Rutherford scattering experiments. Composition of atoms. The structure of modern atom was gotten from the concept of J.J. Thompson and Rutherford works. Atom consists of several subatomic particles like proton, neutron, electron, neutrino, meson, and positron. But the proton, neutron, and electron are the fundamental subatomic particles. That is, they are the major subatomic particles, while the other mentioned particles are regarded as non-fundamental subatomic particles. That is, they are the minor ones. Electrons. Electron was discovered by J.J. Thompson in 1897. It was discovered through cathode ray experiment and is negatively charged. In 1880, J.J. Thompson used a cylindrical tube fitted with two metallic electrodes. This tube is called discharge tube. He passed a very large voltage of about 10,000 volts through the discharge tube at a very low pressure of about 10 power minus 3 millimeter mercury, and this caused a blue ray to emerge from the tube. The ray was called the cathode ray. This is the diagram of the experiment. This is the cathode and this is the anode, the two electrodes that he used. Then this is the vacuum where the air was pumped out, and the voltage, this is the voltage increased. This is what happened. Rays emerged from the cathode. Cathode is negatively charged, and this ray moved towards the anode. So this ray was called the cathode ray. Properties of cathode ray. Cathode ray travels in a straight line. Cathode rays can rotate a wheel placed in their paths, and this is called mechanical effects. Cathode rays are made up of negative particles called electrons. Cathode ray travels with the speed of light. That is, they travel in the same speed with light. Cathode ray causes heat on the object they fall on due to its possession of kinetic energy. When cathode ray falls on an object, it causes heat on that object because cathode ray possesses kinetic energy. Cathode ray causes fluorescence. Cathode ray can penetrate through thin metallic sheets. Cathode ray possesses ionization power. That is, they ionize the gas which they pass through. The nature of cathode ray does not depend on the nature of the gas nor the material used in the discharge tube. That is, the cathode ray does not depend on the nature of the gas nor the materials which discharge tube is made up of. Proton. In 1886, Goldstein discovered proton. Proton is a positively charged particle and is a component of anode ray. Goldstein used a perforated cathode, that is, cathode with holes, in a discharge tube and repeated Thomson experiments. Anode rays pass through the cathode to form a red spot behind the cathode. That is, anode ray passed through the perforated cathode and formed a red spot behind the cathode. The anode ray moved to the cathode, and this is because the anode is positively charged while the cathode is negatively charged. So the anode ray moved towards that perforated cathode and formed a red spot behind the cathode. Properties of anode ray. Anode ray travel in a straight line. Anode rays are positively charged. They are deflected by external magnetic field. Anode rays are affected by photographical plates. Anode rays are particles. Anode rays depend on the nature of the gas in the discharge tube, unlike the cathode ray. Neutron. In 1932, James Chadwick discovered neutron by bombarding beryllium with alpha particle. So the equation is as followed. Beryllium with alpha particle is helium. This gave him carbon-12 and a neutron. So this is a concept of radioactivity, and this led to the discovery of neutron by bombarding beryllium with helium, that is alpha particle. This gave him neutron. Comparison of mass, charge, and symbols of electron, proton, neutron, and positron. This table below gives a summary of it. Electron has the symbol of E with a relative charge of -1 and mass of 9.1 times 10 raised to the minus 31 kg, or 0.000546 AMU, which is atomic mass unit. For proton, proton has the symbol of H or P with a relative charge of +1 and a mass of 1.67 times 10 raised to the minus 27 kg, or 1.00728 AMU. For neutron, neutron has the symbol of N with a relative charge of 0, that is, neutron doesn't have charge, and a mass similar to the mass of proton, which is 1.67 times 10 raised to the minus 27 kg, or 1.00899 AMU. For positron, positron is defined as positively charged electron with the symbol of E plus or beta plus with a relative charge of +1 and a mass similar to that of electron as well, that is 0.000546 AMU. Note: the atomic mass unit AMU is defined as 1/12 of the mass of an individual atom of carbon-12, that is 1.66 times 10 raised to the minus 27 kg. The mass of electron is 1/1837 relative to mass of proton. So from our table, you can see the mass of electron is 0.000546 AMU, while that of proton is 1.00728 AMU. So the ratio of this is 1/1837. Electron has the charge of -1.6 times 10 to the minus 19 coulomb, while proton has a charge of 1.6 times 10 to the minus 19 coulomb. The electron and proton have the same magnitude of charge but opposite. Molecule is the smallest particle of a substance that is capable of independent existence and still retain the chemical property of that substance. Example of a molecule is hydrogen gas, oxygen gas, and nitrogen gas. What is an element? Element is a pure substance that cannot be split into two or more forms by any chemical means. Example: magnesium, hydrogen, zinc, etc. Relative atomic mass. Relative atomic mass of an element is the number of times the average mass of the atom of the element is heavier than 1/12 of the mass of carbon atom. That is the number of times the average mass of an element is heavier than 1/12 of that of one atom of carbon. And the relationship is given as relative atomic mass equal to average mass of one atom of element over 1/12 mass of one atom of carbon. Atomic number. Atomic number is defined as number of protons in the nucleus of an atom. Atomic number is also equal to the number of electrons in a neutral atom. A neutral atom is an atom that neither gain nor lose electron. That is an atom without charge. Mass number is the number of protons plus the number of neutrons of an atom. Mass number is defined as the sum of the number of protons and number of neutrons of an atom, and mass number is also known as nucleon. The neutron number is equal to mass number minus proton number. The atom of an element S can be represented as this, where A, the superscript, is the atomic mass or the mass number, and the Z is the atomic number. Anions are atoms or molecules which has gained electron, that is negatively charged species. Example: fluorine ion, oxygen ion, hydroxy ion, etc. Cation, the opposite of anions, are atoms or molecules which has lost electrons, that is, they are positively charged. Examples: sodium ion, magnesium ion, etc. Problems on atomic number, mass number, electron and neutron number. Identify the mass number and proton number of the following atoms: carbon, sodium, and calcium. Solution: recall the representation of an atom of an element S, where A is the mass number and Z is the atomic number. For I, the mass number equal to 12, while the atomic number equal to 6, which is equal to the proton number. For II, atomic number equal to 11, which is equal to the proton number, and the mass number equal to 23. III, atomic number equal to 20, which is equal to the proton, and the mass number equal to 40. Number 2, find the mass number of the following atom having I, 23 proton and 14 neutron, II, 10 proton and 13 neutron. Solution: mass number equal to proton number plus neutron. Mass number will be equal to 23 plus 14, which is equal to 37. That is for I. II, mass number equal to 10 plus 13, which is equal to 23. Number 3, find the number of electron, proton, and neutron for the following species: I, chlorine ion, II, magnesium ion, III, copper 2 plus, IV, iron metal, V, sodium metal, and Vi, sodium ion. Solution: chlorine ion has atomic number of 20 and mass number of 40. So from the periodic table, you can get this value. The atomic number for chlorine is 20 and the mass number is 40. So atomic number equal to number of proton. So if the atomic number is 20, that means proton number equal to 20. Now this chlorine is gaining 1 electron. That is why it's minus. This is an anion. So for the 20 neutral electron, is gaining 1 more. So this will be 21 electron in total, while the neutron number is the mass number minus the proton number. So it will be 40 minus 20. 40 minus 20, that is equal to 20. II, magnesium ion. Mass number equal to 24. Proton number is equal to 12. Can get this from the periodic table. The mass number for magnesium is 24, while the atomic number is 12, and the atomic number is equal to proton number. So this magnesium is losing 2 electrons. That is why it's 2 plus. So out of the 12 neutral electron, 2 is going out. So it will have 10 remaining. While the neutron is the mass number minus proton number. So this is 24 minus 12, which gives us 12 neutron. Copper 2 plus. Mass number of copper is 64. The atomic number, which is equal to the proton number, is equal to 29. So you can get this from the periodic table. Now this copper is losing 2 electrons. So out of the 29, the electron will be 12 for copper 2 plus. The neutron number is the mass number minus proton number, that is 64 minus 29, which gives us 35. For iron metal, mass number equal to 56, the atomic number, which is equal to the proton number, equal to 26. Then electron, since the iron metal doesn't have any charge, the proton will be equal to the electron, which is equal to 26 as well, while the neutron is the mass number minus proton number. So this is 56 minus 26, which gives us 30 neutron. For sodium metal, the mass number of sodium is 23, proton number is 11. This sodium is a neutral atom, so the proton number equals to electron number. So proton equal to 11, electron will be equal to 11 as well. While the neutron is the mass number minus proton number. So this is 23 minus 11, which gives us 12. For sodium ion, mass number of sodium is 23, proton number is 11, electron is 10. So this sodium ion is losing 1 electron. That is, for out of the 11 supposed neutral electron, 1 is lost. So this will be 10. So the electron is equal to 10, while the neutron is mass number minus proton number, which is 23 minus 11, and this is equal to 12. Atomic species. This table below gives the summary of atomic species. The first one we have here is isotopes. Similarities: they have the same atomic number or proton number and same chemical properties. Differences: they differ in their mass number, neutron number, and physical properties. So isotopes are defined as atoms having the same atomic number but different mass number, and the concept is isotopy. Example: we have hydrogen 1, 2, and 3. The first one is the protium, second one is deuterium, third one is tritium. So these are the isotopes of hydrogen. As you can see, their superscripts are different, that is their mass number, and their subscripts are the same, which is the atomic number. Now, second one we have is chlorine 35 and 37, having the same atomic number but different mass number. Third one is oxygen 16, 17, and 18, having the same atomic number but different mass number. Isobars, the similarities: they have the same mass number or nucleon number. Differences: they define the atomic number, electron, and neutron number, and also chemical property. Example: argon 18, potassium, and calcium. As you can see, their superscripts are the same, that is the same mass number but different atomic number. The third species we have here is the isotones. They have the same number of neutrons, but they differ in the mass number, electron number, proton number, chemical and physical property. Example is potassium and calcium. They have the same neutron. If you check the difference between 39 and 19, 40 and 20, it's the same thing. That means they have the same neutron. Second one is calcium and nitrogen. They also have the same neutron. Calculations on isotopes. The formula is given as relative atomic mass is equal to summation of mass of isotope times percentage abundance over 100. Let's take example. Example 1. Magnesium has 3 isotopes: magnesium 24, magnesium 25, and magnesium 26. The percentage of each in order is 78.7%, 10.13%, and 11.17% respectively. Calculate the relative atomic mass of the magnesium. Solution: recall our formula is given as relative atomic mass equal to summation of mass of isotope times percentage abundance over 100. So for the first one, we take the mass, which is 24, times the percentage over 100. So this is 24 times 78.7 over 100 plus 25 times 10.13 over 100. That's for the second one. The mass is 25 and the percentage is 10. The third one is 26. 26 times 11.17 over 100. Now let's add up. This gives us 1888.8 over 100 for the first one plus 253.15 over 100 plus 304.2 over 100. So adding up, we have 2446.15 over 100. So divide, we have 24.46 gram per mole. So the relative atomic mass of magnesium is 24.46 gram per mole. Example 2. Copper is listed on the periodic table as having a relative atomic mass of 63.55. Reference books indicate two isotopes of copper with relative abundance mass of 62.93 and 64.93. Find the percentage of each isotopes. Solution. Recall our formula. Relative atomic mass equal to summation of mass of isotope times percentage abundance all over 100. So let the percentage abundance of one of the isotopes be Y, while the other will be 100 minus Y. Since we are having two isotopes, if one is Y, the other will be 100 minus Y. Because percentage is usually 100, so the summation of the abundance is 100. So from our formula, our mass number or relative atomic mass is 63.55. So 63.55 will be equal to the first mass, that is 62.93 times percentage abundance, which is Y. So we have 62.93 times Y over 100 plus 64.93 times the second percentage abundance, 100 minus Y over 100. So you have 63.55 equal to 62.93 times Y plus, expanding this bracket, you have 6,493 minus 64.93Y over 100. So we cross multiply. We have 6,355 equal to minus 2Y. So 62.93Y minus 64.93Y give us minus 2Y. Collecting like terms, 2Y equal to 138. So we divide by 2. Y equal to 69. So the percentage abundance of one of the mass is 69 and the mass is one of 62.93. So therefore the isotope with mass of 62.93 has 69% abundance, while the other will be 100 minus 69, that is 31. So the percentage abundance of the mass of 64.93 equal to 31%. Thompson atomic model. Thompson suggested that atom is a positively charged sphere with electron embedded uniformly on it. From the diagram above, this is a sphere with positive charge on it and electron embedded on it. So this is the structure of Thompson atom. Let's see its drawbacks. The model failed to explain the line spectrum of an element and the scattering experiment of Rutherford. Rutherford's nuclear model. Rutherford bombarded a tin gold foil with a high-speed positively charged alpha particle. Alpha particle can be helium, and he gave the following observations. Most of the alpha particles passed without any deflection. This is the experimental diagram. So these are the particles that passed without deflection. This one, they passed without deflection. 2. Some of the particles got deflated. So these are the particles that got deflated. These arrows pointing this word. 3. Few of the particles returned back to their original direction of propagation. So these are the ones that return back to the original path of propagation. Then he concluded that nucleus is small in size and carries the entire mass of the atom. That is the proton and neutron, which is combination gives us nucleon. The extranuclear part contains the electrons, and that is electron revolves around the nucleus. Properties of the nucleus. The nucleus is small with positively charged particles located at the center of the atom. The nucleus contains neutrons and protons, collectively known as nucleons. The size of the nucleus is measured in Fermi. The nucleus is 10 power minus 15 small in size compared to the entire atom. Drawback of Rutherford theory: it does not obey Maxwell's theory of dynamics. According to him, he said that electron revolves around the nucleus. So according to Maxwell's theory of dynamics, if the electron keeps revolving around the nucleus, it will get to a time that the electron will lose its energy and fall back to the nucleus, and this causes the atom not to be stable. So it cannot explain the line spectra of hydrogen. Planck's quantum theory. Planck's quantum theory states that when a body is heated, it emits thermal radiations of different wavelengths and frequency. The radiant energy emitted forms a discrete package of energy called quantum or photons in case of light. The energy of each quantum is directly proportional to the frequency of the radiations. So he gave the relationship E varies directly to V, where E is the energy and V is the frequency. E equals to hV, where H is the Planck constant, and V frequency is equal to C over lambda, where C is the velocity and lambda is the wavelength. So Planck constant is equivalent to 6.62 times 10⁻³ joules per second. So this is the relationship E equal to hV, which is equal to hc over lambda, where h is the Planck constant, v is the frequency, c is the velocity of the electrons, and lambda is the wavelength. Bohr's atomic model. Bohr worked on the essential parts of Rutherford model. He accounted for the stability of atom by introducing the concept of stationary orbit. Recall one of the drawbacks of Rutherford model. He was unable to account for the stability of atom because his theory was unable to obey the Maxwell theory of dynamics. Bohr's postulates are as follows. Atom has a positively charged nucleus, which is responsible for the entire mass of the atom. Electrons revolve around the nucleus in some certain permitted orbit. The permitted orbits are those with the angular momentum of an electron integral multiple of h over 2 pi, where h is the Planck constant. He gave the relationship L equal to mvr, which is equal to nh over 2 pi, where L is the angular momentum or orbital angular momentum, and n is the number of orbits. So this is the relationship L equals mvr, which is equal to nh over 2 pi. H is Planck constant. So n equals number of orbits, which can be from 1, 2, 3 to infinity. The integer n is called the principal quantum number. Electrons moving in a stationary orbit do not radiate or lose energy, and this accounted for the stability of atom. The energy level are numbered as 1, 2, 3, 4 and on, and are called as KLMN. Ordinary electron will continue to move in a particular orbit called ground state. When energy is given to it, it will jump to a higher state called the excited state. So this is the diagram of the energy level, where the center here is the nucleus and these add-up shells are the energy level. So this is K, L, and on, M, and on. So it keeps adding up like that. Bohr's model was able to explain the spectra of species having one electron, like helium plus, lithium 2 plus. Spectral evidence of quantization, that is the explanation for hydrogen spectrum on the basis of Bohr's atomic model. The light absorbed or emitted when electron changes orbit produces spectra as series of lines. For hydrogen, the optical spectra consists of several lines called Lyman, Balmer, Paschen, Brackett, Ford, and Humphrey. Drawback of Bohr's model. It could not explain the line spectrum of atoms having more than one electrons. It could not explain the splitting of spectral line in magnetic field. Note, the Bohr-Sommerfeld model was able to explain fine line spectrum of atom. The Bohr-Sommerfeld model is the modified model of Bohr's model. Dual nature of electron. Lewis di Broglie suggested that light has both particle and wave-like nature. This is true for all matters. Thus, electron has both wave-like and particle nature, and this is called duality of matter. He gave the relationship lambda equal to h over mv, where lambda equal to wavelength and h equal to Planck constant. Mv is the momentum. Planck constant is equivalent to 6.62 times 10 to the power minus 34 joules per second. So this formula can be modified to mvr equal to nh over 2 pi. Heisenberg uncertainty principle. The position and the momentum of an electron cannot be known at any given time. So the Heisenberg uncertainty principle states that it is impossible to know the position and the momentum of an electron at any given moment. He gave the relationship change in S, that is the position, dot change in P, the momentum, is greater than or equal to h over 2 pi. Schrödinger wave equation. The Schrödinger wave equation is based on the dual nature of electrons. Electrons is described in 3 dimensions in an electric field of positively charged nucleus, and the probability of finding electron around the nucleus is given by the Schrödinger wave equation, which is as followed below. For a single particle, the probability of finding the particle at any point is phi square. The Schrödinger equation, provided a set of number called quantum number, which gives the shapes and the orientation of distribution of electrons around the nucleus. So the Schrödinger wave equation gave us the shapes, that is the quantum number that describes the shapes, the orientation of the electrons around the nucleus. Quantum numbers. The set of numbers used to describe the position and energy of electron in an atom is called quantum numbers. Each orbital in an atom is specified by 3 quantum numbers, n, m, l, where n is the principal quantum number, m is magnetic quantum number, and l is the azimuthal quantum number. While each electron is specified by 4 quantum numbers, that is n, l, m, s. S is the spin quantum number. The principal quantum number n, it was proposed by Bohr, denoted by n. It determines the size of the atom by showing the distance between electron and the nucleus. It determines the energy of electron in an orbit. The maximum number of electrons in an orbit is given by 2n squared. No energy in an atom can have more than 30 electrons, where n is the energy level. It gives information about orbits, the KLMN shell. Planck's quantum theory. Planck's quantum theory states that when a body is heated, it emits thermal radiations of different wavelengths and frequency. The radiant energy emitted forms a discrete package of energy called quantum or photons in case of light. The energy of each quantum is directly proportional to the frequency of the radiations. So it gave the relationship E varies directly to V, where E is the energy and V is the frequency. E equal to HV, where H is the Planck constant, and V frequency is equal to C over lambda, where C is the velocity and lambda is the wavelength. So Planck constant is equivalent to 6.62 times 10 to the power minus 34 joules per second. So this is the relationship E equal to hv, which is equal to hc over lambda, where h is the Planck constant, v is the frequency, c is the velocity of the electrons, and lambda is the wavelength. Magnetic quantum number. It is denoted by M. It was proposed by Zeeman. It gives the number of permitted orientation of subshells. The value of M range from -1 to +1. It tells about the splitting of spectral lines in magnetic field. M is related to L by M equal to 2L plus 1. That is, for every M, we have 2L plus 1, where M is the magnetic quantum number and L is the azimuthal quantum number. It gives degenerate orbitals. Degenerate orbitals are orbitals of the same energy. For p subshell, the degenerate orbital is ps, py, and pz. Spin quantum number. It shows the direction of electron and is denoted by s. -half and +half shows the spin rotation or direction of electron. It can be clockwise or anti-clockwise. This diagram below shows the direction of electron. This arrow facing up is the +half and the one facing down is the -half. So electrons are in opposite direction, each half. This is the summary of the quantum numbers and relationships. Let's go through this. N is principal quantum number, which is the shell. L is azimuthal quantum number, which is the subshell. While M is the magnetic quantum number, showing the orbitals. For first energy level, that's N equal to 1, we only have one subshell, which is the S subshell, and it's 0, that is the azimuthal value. And this S subshell only has one orbital, and this name of the orbital is 1s. For the second energy level, we have two subshells, the S and the P. For the S has only one orbital. That is why we are having 0 here. For P has three orbitals, PS, PY, and PZ, ranging from -1, 0 to +1. And the name of this orbital for the S sublevel of the second energy level is 2s, while the P is 2p. For the third energy level, we have three sublevels, S, P, D. That is the azimuthal value, 0, 1, 2. For the S, as usual, S has one orbital, P has three orbitals, PY, PS, PY, and PZ, while D has 5 orbitals ranging from -1, -2, 0, +1, and +2. The S orbital for the third energy level is called 3s. The P orbitals for the third energy level is called 3p, while the P orbitals is called 3d. For the fourth energy level, we have 4 sub-level or subshells. That is S, P, D, F. The azimuthal value is 0, 1, 2, and 3. For the 4s orbital, it only has one orbital. The P has 3 orbitals. That is why I have -1, 0 to +1. D has 5 orbitals. That's why it's ranging from -2, -1, 0, +1, and +2. While the D has 7 orbitals, ranging from -3 to +3. And the name of the orbitals for the 4 energy level is 4s, 4p, 4d, and 4f. Shapes of orbitals. The shape of s orbital. The s orbital has only one unidirectional orientation, and the shape is spherical. So this is the shape of the s orbital. Shape of p orbital. The shape of p orbital is dumbbell, and it has directional properties. That is ps, py, and pz. Those are the orientation. And the shape for ps is in direction of s. This is the sy plane. The shape of ps in direction of s, same as py in direction of y, and pz in direction of z. Shapes of d orbitals. The shape of d orbital is double dumbbell, and it has a directional properties as well. So as you can see, it's double dumbbell. That's why you're having double double. So this is the syz plane. SYZ plane. So this is the name of the orbital, DZS. For the second one, we have DSY. Third one, we have DYZ. Fourth one, we have DZ square. And the last orbital is DS square minus Y square. So these are the 5 orbitals for the D subshells. Shape of F orbital. The F orbital has complicated shape, that is, it has complex shape. F orbitals has 7 orientations, and these are the orientation. The first one is Fs, s square minus y square in brackets, Fy, s square minus y square in brackets, Fz, s square minus y square in brackets, then Fsyz, Fz cube, Fyz square, and Fsz square. So these are the 7 orientation of the F subshell. Rules of filling electron in various orbitals. The first one we have is Pauli's exclusion principle. It states that no 2 electrons in the same atom can have the same value of all the 4 quantum number. That is, if an electron has n equal to 1, l equal to 0, m equal to 0, and s equal to plus half, no other electron in that same atom can have these 4 same value or identical value. So this is what the Pauli exclusion principle is saying. Aufbau's principle. Aufbau's principle states that electrons are added one by one to orbitals following increase in energy. That is, electrons are added from the lowest to highest. This is the energy level, and this is how electrons are added. 1s first because it has lower energy, then 2s because after 1s get 2s, that is the increase in energy, followed by 2p, followed by 3s, followed by 3p, followed by 4s, followed by 3d, followed by 4p, followed by 5s, followed by 4d, followed by 5p, followed by 4f, followed by 5d, and followed by 5f, then continue like that. This is the range for the energy of subshell energy: 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, and on. Hund's rule of maximum multiplicity. It deals with filling electron on equal orbitals having same energy level, that is, degenerate orbitals. Hund's rule of maximum multiplicity states that electron is firstly singly filled before being paired in a degenerate orbital. This minimizes electron repulsion. That is, electrons are filled singly first before being paired in a degenerate orbital. So this is the way electron is filled, and this is the correct way. You want to have 3 electrons to fill in a degenerate orbital, you fill them singly first. So this is correct. And the second one, you have 4 electrons to fill. First of all, you fill singly to occupy all the orbitals. Then the last one, you start again from the beginning and start filling till it exhausted. This is correct as well. Then this last one is wrong. This is a wrong way of filling electron, and this is what the Untitled is saying, that first of all, you have to fill all these orbitals before being paired, but this was being paired first and it was not completely filled. So this is a wrong way of filling electrons. Let's solve problems on proton number and electronic configuration. Number 1, how many electrons can be accommodated in subshell for which n equal to 3, L equal to 1? For L equal to 1, this is the p subshell. So the p subshell is in the third energy level, so this will be 3p. P sublevel has 3 orientation, which we know, the ps, py, and pz. And these 3 suborbitals rather will take in 2 electrons each, so making total of 6 electrons. So our answer to this question is 6 electrons. Number 2, the number of 2p electrons having spin quantum number of -1/2 is, let's see, p subshell has 6 electrons, which we know, the ps, py, and pz, and each orbital contains 2 electrons, making total of 6. For s equal to -half, it means half of the electrons in the p subshell. So this will be what? 3 electrons. So half of 6 is 3. Which of the following quantum number for electron of an atom is possible? Let's see. For n equal to 1, L equal to 0, M equal to 0, S equal to +half. Now we know that n equal to 1 means that this is the first energy level we are dealing with. And this first energy level has one sub level, which is the S, which is correct. And this sub level only has one orientation or one orbital, which is M equal to 0, which is correct. And it can take in 1 or 2 electrons, which is correct as well. So option A is correct. Let's see option B. N equal to 1. Yes, the first orbital, L equal to 1. That is the p sublevel. There is no p sublevel in first orbital. So considering this, option B is wrong. That means option B is not possible. Let's see option C. N equal to 1, the first energy level. L equal to 1, the S sublevel. M equal to 1 orbital. Yeah, correct. S equal to -half. That is 1 electron. N equal to 2, second energy level. L equal to 1, the p sublevel, which can be found in second energy level, which is called the 2p. M equal to -half, which is correct. S equal to -1/2, which is not. So the option that is not possible here is option B. Number 4, write the electronic configuration of sodium. The atomic number of sodium is 11. So recall our energy range: 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, and 5p. So let's write. We are filling in 11 electrons. So we have 1s2, 2s2, 2p6, and 3s1. This is the S. S can take in 2 electrons. The 2s can take in 2 electrons because it only has 1 orbital. The p has 3 orbitals, and each orbital takes in 2, that is 6. So you have 2 plus 2, 4 plus 6, 10. Then the S will take the last electron, which is called the valence electron, that is 1, making total of 11. Recall the atomic number equal to electron number because this is a neutral atom. So we are filling in 11 electrons. So we have successfully filled in the 11 electrons. So this is the electronic configuration for sodium. Total number of electrons here is 11. Write the electronic configuration for calcium. Now let's write, following our energy range: 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. So let's calculate. This is 2 plus 2 plus 6 plus 2 plus 6 plus 4, which is 20. The atomic number for calcium is 20. So, and it's equal to the number of electrons because this is a neutral atom as well. This is 2, 2, 4, 10, 12, 18, and 20. The valence electron here is the outer electron, which is 2. So, valence electron for calcium is 2, and the valence electron that is used for bonding. Number 6. Write the electronic configuration of this ion, Al3+. Atomic number is 13. Atomic number of aluminium is 13. So this aluminium is losing 3 electrons. That's why it's 3+. For a neutral aluminium, the atomic number is equal to number of electrons. But this has charge. That means it has lost 3 electrons. So the atomic number will not be equal to number of electrons. So for a neutral atom of aluminium is supposed to be 13, but now we'll be having 13 minus 3 that is losing. So the electron in this ion is 10. So we fill in 10 following our energy range. So recall our energy range. So let's fill 1s2, 2s2, 2p6, making 10. So we are safely filling 10 electrons. 2 plus 2 is 4 plus 6, that is 10. Number 7. Write the electronic configuration for chlorine ion. Atomic number for chlorine is 17. This chlorine ion has gained 1 electron. So for a neutral chlorine, the electron is 17, but now it has gained 1, making 18. So we are filling in 18, following our energy range. So we have 1s2, 2s2, making 4, 2p6, making 10, 3s2, making 12, and 3p6, making 18. So we have successfully filled in 18. Number 8. Write the electronic configuration for oxygen ion. Atomic number of oxygen is 8. And this oxygen has gained 2 electrons added to the 8 that it has. So we are filling in 10 for oxygen ion. So let's fill. 1s2, 2s2, 2p6, making 10. 2 plus 2 is 4 plus 6, that is 10. Electronic configuration of transition metals. The electronic configuration of transition metals is given as 1s, 2s, 2p, 3s, 3p, 3d, 4s. Not as the usual one: 1s, 2s, 2p, 3s, 3p, 4s, 3d. And the reason is for stability purpose. If you observe, the 3d comes before the 4s, and this particular chain is peculiar to the transition metals. The electronic configuration of transition metals can be written in noble gas form, that is argon 3d4s. If you observe very well, argon has 18 electrons, or the atomic number of argon is 18. So filling in the electrons, it ranges from 1s to 3p. So if you check our chain, from 1s to 3p, this represents argon. They have 3d and 4s. So that's why we write it as argon 3d 4s. Let's take example. Write the electronic configuration of the following: copper, iron, and chromium 2+. For copper, copper has atomic number of 29 and it's a neutral atom, meaning to have 29 electrons. So we fill in 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s1, or in noble gas form, argon 3d10, 4s1. If you observe closely, after the 3 pieces, we have about 11 electrons left. So and these 11 electrons can completely fill the D. So we fill in the D completely before the 4s. So this is 3d10. Then the last electron goes into s orbital, that is 4s1. For iron, the atomic number for iron is 26 and it's a neutral atom. That means to have 26 electrons. So we fill in 1s2, 2s2, 2 pieces, 3s2, 3 pieces, 3d6, 4s2, or in noble gas form, argon 3d6, 4s2. Now, if you observe closely, after the 3p orbital, we have about 8 electrons left, and these 8 electrons cannot completely fill in the d orbital. Then we fill in the s orbital first before the remaining one now goes into the d orbital. That's why we are having 3d6, 4s2. For chromium 2 plus, the atomic number is equal to 24, and for neutral chromium it will have 24 electrons, but this chromium is having 2 plus, that means it's losing 2 electrons. So for chromium ion 2 plus, it will have 22 electrons. So we fill in 22 electrons. So this is 1s2, 2s2, 2 pieces, 3s2, 3 pieces, 3d2, 4s2, or in noble gas form, argon 3d2, 4s2. Now if you observe closely, after the 3 pieces, we have about 4 electrons, and these 4 electrons cannot completely or halfly fill the 3d block. So that's why we fill in the 4s completely, and the remaining one goes into the 3d orbital. Thanks for watching. Please make sure you subscribe, and you can check my channel for other interesting videos. Thank you.